Let us, not let us, solve some cylindrical coordinate triple integrals. So this is what we have right here: cylindrical coordinates. Oh wait, I wrote cylinder for a reason. So this right here is all the information you need to set up a triple integral in cylindrical coordinates. And let's do a little refresher. So in cylindrical coordinates, your x values equal to r cosine theta, just like polar coordinates, and your y values equal to r sine theta, just like in polar coordinates. And z's transformation is just into z. And whenever you're doing something, whenever you're integrating over some volume that looks like an ice cream cone, or that's just the name of the shape, it looks like an ice cream cone, or a cylinder, you use cylindrical coordinates because it's a lot easier to do rather than use some dumb function like square root of x squared plus y squared, and it's very hard to integrate, right? You just integrate a whole number instead. So let's go ahead and do that. We have our cylinder from 0 to 5z, and the radius is 2. And remember, this is a full cylinder. So in cylindrical coordinates, let's write down our triple integral. You're going to have a function, and that function will be z in this case, dv. And remember, dv is equal to, uppercase v, sorry, is equal to r dr d theta dz. Now the order in which you integrate, like this could be r dz, dr d theta, doesn't matter. But never forget the r value here. So this r is part of your function now. So if I set this up, this triple integral, now we have it zr times r d. Let's integrate with respect to z first, and then r, and then theta. So what are the bounds for z value? It's the z value in our triple integral. Well, the bounds for the z value is 0 and 5. Go ahead and write that. The bounds for the r value is 0 and 2 because the radius is 2. And since it's a full cylinder, the bounds for your theta value are 0, pi. Now, if you don't understand why I set up things like this, I have a video called Intro to Cylindrical Coordinates in my Calculus 3 playlist. So before you learn how to solve these triple integrals, you should learn how to set it up as well, or understand at least what the coordinates stand for. Okay, so now that we have the triple integral, what can we do? Well, can we substitute any x or y value here? Well, there's no x or y values, right? So we don't have to write r cosine or r sine for anything. Ignore that. How about any z values? Well, z just substitutes into z itself when you're doing your transformation, so z stays the same. And we also substituted dv with r, dz, dr, d theta. But remember, you have to multiply the function with r. So now that we have all this properly set up, let's move this into the corner. Now that we have all this properly set up, what do we do? Well, we just solve for this like a regular triple integral in rectangular coordinates. All you do, integrate with respect to z first. R is treated as a constant. So when we integrate with respect to dz first, you get z squared over 2 times r. And this is power rule. 0 to 5 equal to z. Now we substitute 5 into here. So when you substitute 5, you get 25 over 2 times r. And 0 substituting the z just turns this entire function to 0, so we don't have to subtract the anything to this. Now this is our new function. We move this function down. Now technically my notation is wrong because I'm omitting the previous integrals, or the latter integrals, but I'm doing this like this because it's easier to understand. There's less things going on. You have 25 over 2r, integrate with respect to r. And remember, I'm just still integrating with my previous order that I set in the top integral. So I do dz first, and then I do dr. If I want to integrate this with respect to dr, all this does is 25r squared over 4. 0 and 2 for your r value. If I substitute 2 into here, I get 100 over 4. If I substitute 0, minus 0. Right, so this is just 100 over 4, and this simplifies into 25. One last thing, integrate with respect to theta. So if I integrate 25 with respect to theta, since 25 is already a constant, all we do is multiply 25 by theta, and our bounds are from 0 to 2 pi. And when we just substitute 2 pi into theta, you get 50 pi minus 0 when you substitute 0. So omit that, and this is our answer for your cylindrical coordinates. For this next problem, you have an x and y value inside of the function, so we have to substitute x and y values according to the transformations given by cylindrical coordinates. Let's go ahead and just do that first. So x squared plus y squared in cylindrical coordinates turns into r cosine theta squared plus r sine theta squared. Now if you substitute out r squared, you get cosine squared theta plus sine squared theta. And this just equals to 1. So it cancels out. You get r squared times 1, which is just r squared. So this is our new function inside of our, or a new integrand inside of our triple integral. So just keep that in mind. And it's also an identity that you can use in polar coordinates. X squared plus y squared is always equal to r squared. And the square root of x squared plus y squared is equal to r. So those are two things that you can just memorize, but our new integrand now is r squared. Let's write that down. And dv, so let's write down dz dr d theta. And that was the previous order we used in the last problem. And don't forget the r. Right? What am I doing? Squared times r dz dr d theta. And if you simplify this even further, you get r to the power of 3 here. Because r squared times r is r to the power of 3. Now that we have this written down, all we have to do is set up the bounds for this triple integral. So we're integrating with respect to z first. So when we integrate with respect to z, the bounds for z are for 0 to 6. That's easy. So that means the height of the cylinder is just 6, and it starts at z level 0. And how about, and let's change this actually, y greater than 0. And let me try to explain this with visuals this time. Let's say you have a coordinate system. This is x, y, and this is z. And you have a cylinder like this. If you want your y value to be greater than 0, let's extend this. Your positive y-axis, right, is on this side of the coordinate plane. Let's extend for the negative z as well. Is on this side right here. Therefore, your cylinder looks something like this, where, oh, I can't believe I erased everything here. It's crooked. Where your cylinder is only a half cylinder on the positive it's kind of a bad drawing, but it's only a half cylinder on the positive y side. Sort of something that looks like this. If I could draw it better. But that means your theta values are from 0. So 0 starts on the x-axis. So this is the theta value of 0. And if you rotate this by radians of pi, your theta value is limited by 0 and pi, because your cylinder is only on the positive y-axis. So your theta bounds are from 0 to pi. And your radius is just 3, so your bounds for r is just 0 and 3. Now that we have the triple integral set up, all I have to do is solve for it. Let's do that. First, we integrate with respect to z. Right? Since r cubed is treated as a constant, this is just z times r cubed from 0 to 6 for z. If you substitute 6 in, you get 6r cubed. Let's integrate. This is our new integrand, so let's integrate with respect to r now. dr. If you integrate this with respect to r, you get 3 over 2 r to the power of 4 from 0 to 3. If I substitute 3 into 4, let's see, 3 to the power of 4 is 81. And 81 times 3 is 243 over 2. One last thing, we integrate this with respect to our theta value. So 243 over 2 is just a constant, so we multiply that by our theta value. And our bounds are 0 and pi for theta. And we plug in pi here, you just get 243 pi over 2. For this next problem, something is going to be just slightly different, and that is one of our functions, one of our bounds is a function. So z is bounded by square root of x to the power of 2 plus y to the power of 2. How do you change this in the cylindrical coordinates? Well, it's the same exact thing as how you would change your function in the cylindrical coordinates. So you would just extract your function as a bound and just substitute in your values. So x is substituted as r cosine theta squared plus r sine theta squared. You square root all of this. Remember, in the previous problem, we've established that x squared plus y squared is equal to r squared. And the square root of x squared plus y squared is equal to r. And I derive this by just square rooting both sides here. So the square root of x squared plus y squared is simply r. Therefore, our z bound is just r. Our radius is 3, and now we have a full cylinder. And this function is the same integrand as before, so our triple integral was already established as r to the power of 3. dz dr d theta. Quick reminder, how did I get r to the power of 3? X squared plus y squared is equal to r squared. But dv is equal to r dz dr d theta. So I multiplied r squared by an r value to get r to the power of 3. Let's move on. Now we find our z bounds. Our z bounds are 0 and r now. And our r bounds are just the radius, so from 0 to 3, and our theta bounds is a full cylinder now, so we have 2 pi as our theta bound. What do we do next? Well, we integrate with respect to z first, as always. Now you don't always integrate with respect to z. doesn't matter what order you integrate with respect to. But as long as it's possible to integrate it. So our r bound is the upper bound and a 0 is our lower bound. If we substitute r into z, we get r to the power of 4. Simply our new integrand. Now we integrate with respect to r. So r to the power of 4 with respect to r with power rule is just r to the power of 5 over 5. Our bounds are 0 and 3. We substitute 3 into r, and then we get, I'm using my calc real quick, 243 over 5. Our new integrand again, and then all we do is substitute, not substitute, integrate with respect to theta now. If you integrate with respect to theta, all you do is just get your integrand multiplied by theta. And now that we have this, multiply this by 2 pi, original function by 2 pi, by substituting in for theta. So I just brought this down like this. And you get 486 pi over 5 as your answer. Let me double check if that's right in my notes. Yes, sir. Now, this problem is a little tricky. And that is because we are not given the bounds for radius. You will see some problems like this, possibly on your exams. I have finals like literally next week. I don't know why I'm not studying and why I'm making a YouTube video. But, oh yeah, I probably won't be able to make videos next week then. I'll still make them. For you guys, of course. Okay. But this problem is just slightly more tricky because your radius is radius bounds, or your radius isn't explicitly given to you. Like previous problems, I would say the radius is like 3 or something, right? Now we're not given the radius. How do you find your radius bounds? Well, it's actually a lot more simple than you think. So let's check if we can substitute anything first. Again, our integrand already is in cylindrical coordinates because z is equal to z, so we leave this alone. Now let's go find our bounds. So whenever we have bounds that aren't in cylindrical coordinates yet, we can actually substitute this to turn into something else. Let's use different colors on the last problem. I don't know why I didn't use it in the previous ones. But x squared plus y squared is already established to be r squared. So our lower bound is r squared, and our upper bound is 4. Well, what we can do here, actually, it always helps to draw a graph, is, well, draw a graph. And if we draw this graph, we can actually picture or visualize what our bounds look like. Let's say this is the r axis and this is the z axis. R squared is a simple parabola. So let's draw the simple parabola. Wait. I think I know how to do this. Oh. Wait, that's a tool. Okay, this is a simple parabola. Okay? And this simple parabola is the function of z equals r squared, right? And our upper bound is given by the function z is equal to 4. So it's just a straight line in this graph. Go ahead and write that down. Z is equal to 4. So what are the bounds for r if your z equal to 4 is your upper bound? Well, technically this is sort of the region that we are looking at when you're talking about this inequality. But we need to find our r bounds as well. So what's the r bounds? Well, r squared is equal to z, and z is equal to 4. So we can actually substitute z into each other, so you get r squared is equal to 4. Therefore, the bounds for r is just equal to plus or minus 2, but r must always equal to a positive number. So the bounds for r is, or your radius, is just 2. Therefore, when we set up the integral, zr dz dr d theta, our z bounds are r squared, right, and 4, but our radius bounds are from 0 to 2, because that is when our function of r squared intersects with 4 at this point right here. Now, this actual function is in 3 dimensions, right? But I'm representing it in a 2D plane because it's, well, it's technically the exact same thing. This is just a cross section of what you are looking at in 3D. So keep in mind what we did was turn all our bounds into cylindrical coordinates. And then what we did after that is draw a graph with these two functions. Let's just say r in this case is x and z in this case is y, because that's their corresponding axes. And we just drew a function and we waited to see if when r squared intersected with the function 4. And that is at 2 right here. And r always has to be positive, so it's not plus or minus 2. Now that we have that, our theta bounds shown already and given was 2 and 2 pi. 0 and 2 pi, sorry. So this is our integral that we have to solve. Let's solve this. If we integrate our function, this is r squared, z, r with respect to z, dr d theta, you get z to the power of 2 over 2 r squared and 4 as your z bounds. This is z, not a 2. So when you substitute 4 in, because you always integrate with the upper bound first, substitute 4 into here, you get 16 over 2, which is just 8r. If you substitute r into here, you get minus r to the power of, wait, this is 4, 16, 8, yeah, r to the power of 5 over 2. Now this is our new integrand. So now we integrate with respect to r. Minus r to the power of 5 over 2 dr. We integrate this, we get 4r squared minus r to the power of 6 over 12 from 0 to 2 for our r bounds. We substitute 2 in, you get 16 minus 2 to the power of 6 is 64. And 64 over 12, well, I don't need to worry about that, because if you just simplify all of this, hopefully you know how to simplify fractions, but if you simplify all of this, you get, see, it says 128 over 12, which simplified further is equal to 32 over 3. Now this is our new integrand. We just have to lastly integrate with respect to theta. Let's go ahead and do that. Our bounds are 0 and 2 pi. 32 over 3 d theta is equal to 32 over 3 theta. Excuse me. Theta is our bounds, and all we do is plug in 2 pi. So you get 64 over 3 pi as your final answer. So as always, if you have any questions, put it down in the comment section. Everyone have a fantastical finals if you're taking that right now.